Hello, this video is going to be on thin film interference. So thin film interference is a phenomenon where light basically interferes with itself to where it can produce different colors when it reflects off a thin film. And so examples of this are like a bubble, or like a layer of soap or oil on water. So when you have like a bubble and you look at it, it doesn't just look clear or white, even if the light shining on it is white. You see different colors on it. So like you see some like magenta or cyan or green or yellow or blue or something like that. So it's like and same thing with like oil on water. You can see like the colorful pattern of it because of thin film interference and the way it produces different colors based on the thickness of the layer of material or medium that the light is reflecting off of and through. And so before we discuss how thin film interference works exactly, we need to review a few concepts with light. And so the first thing we need to review is superposition and interference in general. So whenever you have two light rays, interference happens when two light rays interact, basically. So let's just say you have two rays that are in phase, and we'll represent them as waves. And in phase means that they just line up. So you see that the peaks and troughs of both of these light rays are in the same locations. So by superposition, when we add these light rays together, um, their peaks will add and their troughs will add, and so your resulting light ray will be something like this. So it'll get amplified. So this is constructive interference. And so this happens again when they are in phase, which means that the wavelengths are the same, and or the frequencies are the same, and that the peaks and the troughs line up. Now, destructive interference, or like completely destructive interference, occurs. So this is destructive when the peak of one light wave lines up with the trough of another light wave. And so one of them might look like this, and then the other one will be inverted from it. And so you see here that the peak lines up with the trough of the other one. And when you add these together through superposition, they all cancel out, so you just get nothing. And so by destructive interference, light these two light rays cancel each other, and so nothing you don't see anything when they destructively interfere. And this is how thin film interference works. It's because some colors, because of depending on the thickness of the film and the angle at which you view it at, certain colors, because the wavelengths change with different colors, will cancel out with certain thicknesses of film. And so when that cancels out, let's just say that the green like color cancels out because its thickness of film at that space is the right thickness to where it cancels green out. Then red and blue will still get reflected, but green won't because it destructively interferes with itself. And so what you see is going to be a magenta color. And then since the thickness of films usually vary a little bit, the reflected colors will also vary. And then that's why you see like that rainbow type of pattern. Um, and now we'll see exactly how the thickness determines what colors get reflected and which don't later though. Okay, so and then now when we're talking about these waves, we can say that this bottom wave or the top wave, they're offset by, so the offset here, sorry, offset is half a wavelength. Because remember, one wavelength is one complete cycle here. So this is one wavelength. Now you see that the second wave is going to be half a wavelength offset in one direction from this first wave. And that's what allows it to destructively interfere. And then this can also be called 180 degrees out of phase. So, or a 180 degrees phase difference. Because when you think about these waves, you represent them with like a sine or cosine function. And a cosine function or a sine function is periodic every 360 degrees, which means that this function repeats every time the input value uh, goes through 360 degrees. And so if we write like a sine function as sine of theta plus phi, where phi is the phase, sine, so for phi equals 0, you just have like this normal sine function. But then for phi equals 180 degrees, you start halfway through the cycle. So remember this, for phi equals 0, this would be sine of 0 degrees. This is sine of 90 degrees. Or sorry, this is sine of 180 degrees. And this is sine of 360 degrees, which again returns back to the 0 value. Now, if we start off with a 180 degree shift, then at theta, so this is theta, at theta equals 0, it's really the value at 0 plus 180 degrees. So the sine function then looks like this. And then we see here that this is the same as half a wavelength further. Sorry, this isn't perfectly drawn, but this is destructive interference because this function is shifted by 180 degrees or half a cycle or half a wavelength as we see here, which causes it to destructively interfere. Okay, another thing that we need to review here is how the wavelength of light changes through a medium as it goes to different mediums. So, when light changes mediums, when light changes medium, the frequency stays the same. So we have here frequency is constant. So the frequency of the light doesn't change. So like the color of the light wouldn't change. And you see this in everyday life. Like if you pass like one color of light through glass, assuming the glass is clear, or like a color of light through clear water, the color of the light doesn't change, but the speed of the light changes, and so speed changes, so velocity changes, and then so that depends on the property of the material, and then we write the index of refraction here. So index of refraction, index of refraction is equal to, so that's n, the variable n is the index of refraction, is equal to the speed of light in a vacuum, which is c, divided by the speed of light in that material, which is v. And then we have c here is roughly equal to 3.00 times 10 to the 8 meters per second. And then, so light, this is the fastest light can go. And then in some materials, light will slow down, and it will slow down to different degrees. So in air, it basically travels at the same speed. So for air, n is roughly equal to 1. It's actually a little bit higher than 1 since light does travel a little bit slower in air than in a vacuum. But it's like very small. It's like really slightly larger than 1. So it's like 0.00. I forgot how many it was, but it's essentially almost 1 for practical purposes. But like for water, n is about 1.33, and that just basically means that light travels 1.33 times slower in water than air because you're dividing by 1.33 to get the velocity of light in water. And so this is the index of refraction. But then, since velocity is equal to frequency times wavelength, if velocity changes, then the frequency stays the same, then the wavelength also has to change. And so if you have c is equal to the frequency of light times the wavelength in a vacuum, we'll call it n naught, and then v is equal to this, then you have your index of refraction is equal to the frequency times the wavelength of light in a vacuum divided by frequency times the wavelength of light in that medium. And so the f's cancel out here, and then this is just equal to the wavelength of light in a vacuum divided by wavelength of light in a medium. So this means that for if something has an index of refraction higher than 1, that means that its wavelength so its wavelength will be longer, or sorry, yeah, so if the index of refraction here is higher than 1, then the wavelength will be shorter inside the medium than in a vacuum. And that makes sense because if frequency stays the same, then if velocity decreases, then the wavelength of light will decrease. And so wavelength of light in a material with an index of refraction greater than 1 is shorter than wavelength of light in a vacuum of the same frequency. And this will become important later in our calculations. And then finally, we have Snell's law here for describing how light gets refracted through materials. So in refraction, when you have light passing through a material, so this is N1 and N2, let's just say for this sake that N1 is less than N2, then when light passes through this material, it will refract or change angles. And this angle here, if we write this as angle theta, where theta 1 is going to be the angle of the incident light ray to the normal line of the surface, and theta 2 is the refracted light ray to the angle to the normal line of that surface, then Snell's law states that so n1 sine theta 1 is equal to n2 sine theta 2. And basically this, if you think about this mathematically and what it means that if n2 is greater than n1, then the sine theta has to be less than, sine theta 2 has to be less than sine theta 1. And so theta 2 is smaller than theta 1. And so for if n2 is greater than n1, then this normal or this light ray bends towards the normal line. And if we flip this backwards, so like n1 is greater than n2, you can think about this going as in reverse. Then if you're going from something with a larger index of refraction to a smaller index of refraction, then the light bends away from the normal line. Okay, so now that we've reviewed these concepts, we can start going over how thin film interference actually works. And so we can illustrate thin film interference with 3 different mediums. So basically you have medium N1, which we'll assume is air. And then so that means that N1 with refractive index N1, so that's roughly equal to 1 here. So the refractive index of this is roughly equal to 1. So that's the boundary. And then here is another material, call it N2. And now we have N2. N2 is going to be greater than 1. And then we have another material on the other side, N3. So N2, this material is going to be the thin film. So there's a thin film of material with refractive index N2 separating N1 and N3. So you can think of this as like a bubble where N1, this here is air, and this here is air, and then this N2 film is going to be like the surface of the bubble. Or you can think of this as like oil on water, where N1 is air, N3 is water, and N2 is a thin layer of oil on the water. And so when we have an incident light ray here, so let's draw an incident light ray. It'll look like this, and then it partially reflects and partially refracts. And so light, it doesn't completely refract through, it also partially reflects through. So like when you shine like think about shining like a beam of light through water, you can still see the reflection of the light where it hits the water, but then some of the light also goes through the water. And so if you remember the video where I covered physical waves, if you have something, if you have a wave going through from a heavier medium to a lighter medium or vice versa, part of the wave gets transmitted through and part of the wave actually reflects back. And so this light ray splits into two almost. So where it partially reflects, it partially reflects back out and then partially refracts through. Now, this, when it hits this other boundary here, the same thing is going to happen, where it partially reflects back and partially refracts through. Now, depending on N3, if N3 is greater than N2, then this will bend closer to normal. And if N3 is less than N2, then this will go back outwards further from the normal. So either of these could happen. I'm just going to keep one of them for now. We aren't really concerned with this other light ray for now. We're just concerned with this side. So once this hits the first boundary again, it's going to partially get transmitted through like this. And these are going to be at the same angle here because of Snell's law. And then partially gets reflected back down. And then this keeps going really, but then we only really are concerned with these first two because that's where the most like, or like that's, we can just calculate the property of how interference happens with these first two reflected rays or refracted rays, however you want to think about it. So if we look at these angles here, we can label them as, this angle is theta 1 from Snell's law, and then this angle here will also be theta 1. And then this angle, sorry, the angle to the normal here will also be theta 1. And now these two angles are both theta 2. So these angles are both theta 2, again by Snell's law. And then this is theta 2. As you can see, because these are alternate interior angles. So by Snell's law, this has to be theta 2, and then these two have to be the same. And now, if we draw a line right here, and this line will be important for comparing the distance that the light travels, or the difference in distance between these two rays. If we draw this line here to where it's perpendicular to the first ray, and meets where the second ray comes out, we can actually see that this angle right here is also going to be equal to theta 1. And then there's multiple ways that you can see why this is true. For example, this angle and then this angle have to add up to 90 degrees. And then this theta 1 and this angle have to add up to 90 degrees. And so that means that these two angles have to be the same. So they're both theta 1. And then we can extend this line out a bit further. So when we're looking at interference, we want to see how far offset these two waves are. And so thin film interference occurs with interference between these two rays. And we want to see how far offset these two rays are from each other. So starting from this point where it first contacts, we can compare where they're parallel here. So we can compare the offset of this first ray with the offset of this second ray. And so this first ray travels this distance right here. So the first ray travels this distance right here. I'll draw it in another color. So the first ray travels this distance right here in green. Now this green distance, so ray 1, this green distance is going to be equal to the sine of theta 1 times times this length right here, right? And that length right here is going to be equal to 2 times the tangent of theta 2 times d. And so the thickness of this film, let's call it d, this length, this green length right here on the bottom is going to be equal to 2 times the tangent of theta 2 times d, because this length right here is also d. So tangent of d, tangent theta 2d gives this half of this length, and so this full length is equal to 2 times tangent theta 2 times d. And then so we want to see this length of this green section up here, then this ray 1 travels a length of sine theta 1 times 2 tan theta 2d. Okay, so that's the distance that this ray 1 travels. Now if you want to see the distance ray 2 travels, it's just going to be equal to this distance right here, so like this V shape. And we want to compare their offsets when they're parallel like this. And so this V shape, ray 2, is just given by d divide, or 2 times d divided by cosine of theta 2, because cosine of theta 2 is d over one of these blue distances. And so this blue distance is going to be equal to d divided by cosine theta 2, and then it goes down and back up, so it's 2 times d divided by cosine of theta 2. Now remember how we see that the wavelength of light changes when it goes to a different medium. So when we're comparing these offsets, we don't compare the actual distance that light travels. We want to compare how far offset their wavelengths are. So when light goes to a different medium, all right, so when light travels through a different medium, so the wavelength gets compressed. So the wavelength gets compressed by n, right? Because that's our index of refraction. However, if light travels one wavelength, so since we're comparing wavelengths, though, we care about how many wavelengths it traveled while in this medium. And so if light gets compressed by n, we need to scale this distance by a factor of n to undo this compression in air. So if it travels one wavelength in this medium, and it travels one wavelength in air, we want those two to be the same offset, since we're trying to find the offset of their wavelengths. But if the wavelength in this material is shorter than this wavelength in air, then we need to scale it back up so that their wavelengths match again, so we can compare them correctly. So since the wavelength gets compressed by n, traveling a distance x, so if you travel a distance x, traveling a distance x in this medium is equivalent to traveling a distance nx in a vacuum. So and this is because if it travels a distance x, so if it travels one wavelength in the medium, it'll actually travel the wavelength in a vacuum divided by n. And so if that's one wavelength, then in air, one wavelength will be equal to n times x to rescale. So basically, since the wavelength compresses by n, you have to stretch it back out by n again in order to compare it correctly to light that travels in air. And so this distance here, ray 2, even though it travels 2d divided by cosine theta 2, in air, it would be the same as if the light traveled, effectively traveled, so 2n2d divided by cosine theta 2. So light traveling this distance inside the medium, it travels the same number of wavelengths as light traveling this distance in air. And so if we want to find the difference or the offset here, so we find the offset, we see that the second light ray travels further than the first light ray. And so the second light ray is given by 2 and 2d divided by cosine of theta 2. And so we have the offset is equal to 2 and 2d divided by cosine of theta 2 minus this distance that the light ray travels. And so if we want to find the difference between them, so we minus the distance, subtract the distance that the first light ray travels in air, so that they start at the same place. And this is going to be equal to 2d tan theta 2 sine theta 1. Now we can make a few substitutions here. So tan theta 2 is just equal to sine theta 2 divided by cosine theta 2. And sine theta 1 is equal to n2 sine theta 2 over n1 by Snell's law. However, since n1 equals 1 for air, or it's basically equal to 1 for air, we get that this is just equal to n2 sine theta 2. And so making these substitutions, we get that our offset is going to be equal to 2n2d divided by cosine of theta 2 minus 2d sine theta 2 divided by cosine theta 2 times n2 sine theta 2. Now if we factor out a factor of 2 n2d, so this is equal to 2 n2d, if we factor that out, we get, and then there's also a common factor of divided by cosine theta 2, so cosine theta 2, we get this is just 1 minus sine squared theta 2. And sine squared theta 2, this is trig identity, so a Pythagorean trig identity, and then this is just equal to cosine squared theta 2. And so if we simplify this, we get that this is just equal to 2n2d cosine squared theta 2 divided by cosine theta 2, which is just equal to 2n2d cosine of theta 2. So this is the offset, or this is the difference between these two rays right here. And so we see that if this offset here is one wavelength, or if it's an integer multiple of the wavelength, then these two rays will line up, and then it'll constructively interfere. Or if the offset is half a wavelength, it'll destructively interfere. However, that's not completely correct yet, because we have to take into account the properties of light as it reflects through different surfaces. And so if there's two different scenarios that we could come across here. So we could come across a scenario where n1 is less than n2 and n3 is also less than n2. And so this basically means that you have a material here where this is n1, n2, and n3. You have a denser film sandwiched between two less dense materials. And so this is like a bubble. So for like a bubble, you can have N1 and N3 is air. Um, it doesn't have to be. This is just an example, but this could be like N1 and N3 is air and N2 is soap. And so if you have that, then what it looks like is you have this instant ray, and then it gets reflected, and then this will bend towards the normal here, and then this will bend away from the normal again, bend towards the normal, and then here's our rays. So if we remember from the physical waves video, whenever you're going from something that's less dense to more dense, this light here actually inverts. So this inverts. So remember, so when you're going from something less dense to something more dense, so a more dense material here, when you have a wave that goes like that to the more dense material, it'll get reflected inverted. So the reflection here will be inverted. So this inverts right here. However, this side does not invert. And so because it's going from more dense to less dense. So if you remember, I'll draw this with a different color actually. So a more dense is going to be red. So if you're going from more dense to less dense, sorry, so this, if you're going from less to more dense, this ray, so the wave inverts when it gets reflected. However, if you're going from more dense to less dense, it does not invert. So if this is going like that, then going back, it will look like this. So it doesn't invert. And so this does not invert. Now, since it inverts once, an inversion is the same as a 180 degrees phase shift. And so if there's one inversion, then there's an 180-degree phase shift, which means that if the offset is a multiple of the wavelength and it inverts, it's essentially the same as adding half a wavelength to it. So an inversion is equivalent to adding half a wavelength. And so for destructive interference, it occurs when it's half a wavelength offset, or it's between two integer wavelengths. And so this distance here, so the offset, again, is equal to 2n2d cosine of theta 2. And now when this offset is equal to half a wavelength here, plus, so when it's equal to m times lambda, so when it's a full integer multiple of a wavelength, then the total offset is going to be equal to this distance it travels. I'll call this the difference now. So when it's a full integer multiple of a wavelength and you add the inversion, then this is destructive interference. So this would be destructive interference. And so m is a natural number. So it's like 1 or 2 or 3 dot dot dot, or like a whole number, not including 0. So destructive interference occurs whenever you have a dense material sandwiched between two less dense materials, and this m value here is a whole number. And so because it only inverts once, we want this offset to be 1/2 of the inversion plus a whole number of wavelengths. Now, if we assume that cosine, or if we assume that theta 2 is small, so if theta 2 is small, so theta 2 is much less than 1, And then this can happen either, so from Snell's law, this can happen either if theta 1 is small or if this n2 is big, or both. So if theta 2 is small, then cosine theta 2 is roughly equal to 1. And so we can say that 2n2d is equal to m times the wavelength, or this thickness of the film d is equal to m divided by 2 times the wavelength divided by n. And now if we remember back up here, the wavelength divided by n is just going to be equal to the wavelength of the light inside the medium. So the wavelength divided by n here is just equal to the wavelength inside the medium. And this makes sense because if it's traveling 1/2 of the wavelength inside the medium, then if the thickness of the film is 2 times the effective the wavelength inside the medium, then it will travel 2 wavelengths, and so it'll be a whole number of wavelengths off distance plus the inversion, so it'll have destructive interference. So this is for, again, this equation works for n1 is less than n2 and n3 is less than n2. Now, if we think about the situation where n1 is less than n2 is less than n3, so this can be like oil on water. This is an example of it, to where if you have n1, n2, and n3, then when we have an instant light ray here, redraw that. When you have an instant light ray, it gets partially reflected and partially refracted, and then over here, it gets partially reflected, this gets refracted, and then this gets partially reflected through again like that. Since it's going from less dense to more dense, this inverts. And then since it's going from less dense to more dense again, this also inverts. So since it inverts twice, it's the same as having no inversion at all, because it's like flipping it and then flipping it again. And so it's the same as not flipping it at all. So this means that destructive interference occurs. So like these, the angles and everything is still the same. So our distance here is still going to be equal to 2 n2d cosine of theta 2. But then this is destructive if it's m minus 1/2 times a wavelength. So if it's 1/2 offset from an integer multiple of the wavelengths, then it'll be destructive because the inversions, since there's 2 of them, they cancel out. And so it's destructive if they're 1/2 a wavelength apart or 180 degrees out of phase. And so with 2 inversions, you have to have this factor of 1/2 here. Or not a factor, but you have to have this offset of 1/2 in the distance, 1/2 wavelengths. And so again, if we assume that theta 2 is small, then you have 2n2d is equal to m minus 1/2 times this wavelength. And then if we move things around a bit, we get that d is equal to 2m minus 1 divided by 2 times this wavelength in a vacuum divided by n. So again, this is going to be the wavelength inside the material. And then this here, notice that this section right here, 2m minus 1 is just any odd whole number. So this can be 1, 3, 5, 7, or on and on and on. Um, so so if this m is any odd whole number, then using this formula, you can get the distances that will destructively interfere. So this is destructive interference. You get the thicknesses of film that will cause destructive interference for this wavelength of light. And so if you're given a wavelength of light and you want to find the thickness of film that will cause it to destructively interfere, first you have to find if that film is going to be on top of another denser material or if it's going to be on a lighter material. And then based on that, you can use these formulas here to find out what thicknesses of film will cause destructive interference. Now, if you want to find constructive interference, or these two light rays will reflect brightly because they're aligned, you just have to subtract a 1/2 from here or add a 1/2 from here. So for constructive interference, so if you have n1 is less than n2 and n3 is less than n2, for constructive interference, again, this is where it reflects brightly, you get 2 n2d cosine of theta 2 is equal to m minus 1/2. So this is removing the effect of the inversion times the wavelength. So again, this is like this formula right here. So in the end, you get d is equal to 2m minus 1 over 2 times this wavelength divided by n. And so this is for constructive interference whenever you're sandwiching a thin film between two lighter materials. And then for constructive interference, for n1 is less than n2 is less than n3. If you want constructive interference, since there's two flips, you want the distance or the difference between the distances to be a whole number multiple of the wavelength. And so you get 2 n2d cosine of theta 2 is equal to just m lambda, and then you get d is equal to m over 2 times lambda over n. And so, I made a mistake. This should be a 4 on the bottom. I forgot about the factor of 2 here. So for destructive interference, whenever you're going from one material to a denser material to an even denser material, it should be 2m minus 1 over 4 times lambda over n. And then for constructive interference here, so this should also be a 4 here on the bottom. So it's any odd integer over 4. And then this here, again, any odd integer over 4 for sandwiching a thin film is going to give constructive interference. And any integer over 2, if you have dense to so when you're going to denser to materials, so when n2 is denser than n1 and m3 is denser than n2, you get that this formula gives constructive interference. So it's basically just flipped from the destructive interference. Okay, so this is how you calculate thin film interference for different materials.